Mic tests 1 2. Okay, so hello. Kwa majina naitwa Andrew and I'll be presenting number 1 A and B. I hope I'm audible. So to question 1A, how is it possible to make a modulo 2 power n counter using n flip-flops? So this question basically is asking the process of making a counter from flip-flops. And now the problem is how I want to show you, but imeshindikana. So anyway, so I'll read the process, and in some questions baadaye mtaona how it is done. So the process of making a counter, you start with a state diagram. A state diagram shows all the possible states that the counter is supposed to go through. All that can be found in page 183 to 185 of the Professor Mwangi's book. Yes. So anyway, so number 2, after you get the possible states and you put them in a state diagram, you will get the characteristic and excitation table for the specified flip-flop. There are 4 types. If I remember my first sem, that was SR, JK, T, and D. Yes, so you get the characteristic and excitation tables. Then you generate the excitation table for the counter. So the excitation table is basically shows the present state, then the next state, and the inputs that you're supposed to get. Now the inputs you'll get from the excitation table of the flip-flop. And after you've done all that, you'll generate, okay, you'll get the minterms from the table. So you generate logic equations by searching for the minterms via a Kano map. Yes, I hope everyone knows what a Kano map is and how to use it. Only first semester. Anyway, so after you've generated some logic equations, those equations is what will guide you on what you put as the, should I call them logic circuit, the gates and the connections required. Yes, and that's the process. That's how it's possible. The 2 types of such counters is basically synchronous and asynchronous counters. So modulo 2n basically refers to an n-bit binary counter. So any binary counter that has n flip-flops is a modulo 2 power n counter, where n is the number of flip-flops. Any questions? Hi. Question 2 is what is currently you're seeing on your screen. So the question is, differentiate between PROM, PLA, and Ttl, where PLA stands for Programmable Logical Array, and PAL stands for programmable array logic. Prom is programmable ROM. In terms of their and or arrays and matrices. So prom has a fixed and array, but a programmable or array. In programmable logic array, both the and the or arrays can be programmed. But in programmable array logic, the or array is fixed and the and array is programmable. Yes, so hapo hakuna mambo mingi, hivyo tu ndio venye iko. And I am done. Any question? Haya, sawa. On to the next speaker.
Hi guys. I hope you can all hear me. And
yeah.
Oh, okay. So okay, so question C. A microprocessor uses RAM chips of 1024 by 4 capacity. We decided to use 4, although we can't see what number it is. So how many chips will be required to obtain a memory of capacity of 16 kilobytes? So we know that 1 kilobyte is equal to 1024 bytes, and 1 byte is equals to 8 bits. So also this 1024 by 4 here stands for 1024 memory locations with a 4-bit pattern. So we know for sure this 1024 by 4 is in bits. So we need to have the 16 kilobytes in the same dimensions as this 1024 by 4, or you can change the 1024 by 4 to kilobytes, whichever you want. So 16 by 1024 by 8 gives us this figure here. And when you divide by 1024 by 4, you'll get 32 chips. Yeah, is there any question? Hello.
Hello.
Yeah.
Over there where you are dividing by 1024 times 4. Why do you have that 4 there? Isn't that 4 just the number of output like lines from the RAM chip?
Yeah, yes. Okay, yeah. And
isn't only the 1024 the number of like memory locations in each chip?
Okay.
Yeah, so because it's the same as the one with our group was doing for number 4. And I saw that problem.
Oh, okay, I've seen it. Okay, I don't know. I'll have to check to answer you. I cannot answer you on the top of my head right now, but I believe it's Yeah, I believe it's the 1024 by 4. You have to multiply, but I will give you the reason before this session ends.
Okay.
Yeah. But yeah, good question. Yeah, I didn't think of that. Yeah, so yes, and Yokabi will do part 2. Or is there any other question apart from that one? Okay.
Oh, hi guys. I hope you're all well and you can hear me. So,
Yes.
okay. Let me present. Okay, can you guys see?
Yeah.
Okay. So I'm going to do part 2. Although, okay, now that Sean posed that question, we'll look into it. But okay, let me just present what we did. So the question was the number of chips and number of address lines to provide capacity of 1024 bytes. So just like what Kamara said, to change the bytes into bits, you multiply by 8. And then so, okay, in this case, we divided 1024 divided by 1024 times 4, because, okay, as we were doing this, we thought that this would just be equal to the total number of bits. But okay, now that Sean has asked that question, we'll look into it. So if you do the math, we got 2 chips. And then the next one was the number of address lines. So just as Kamara said, we had 1024 memory locations. And in order to get the number of address lanes, usually do 2 to the power of okay, no, wait first. To get the number of memory locations, it's usually 2 to the power of the number of address lines. That's what gives us the number of memory locations. So now we want the number of address lines. So you just do log on both sides, and we got 10 address lines. Yeah. So how we're going to do the next part, B and C. Kamara is supposed to be presenting D, and then I'm supposed to present E, but I think maybe just to make things easier, I'll just present E, and then now she can come back and finish up with D. So, okay, so the question okay, so the question was, if I'm not wrong, it was what are synchronous counters, and then we were supposed to design a mode 5 synchronous counter with JK flip-flops. I'm not wrong. I'm waiting for the question paper to load, but that was the question. So okay, so okay, I didn't write it down, but synchronous counters are are counters that a single clock pulse is used to change the beats of the counters simultaneously. So that's what synchronous counters are. You have a single clock pulse changing the beats of the counter simultaneously. And then, okay, it hasn't loaded. Okay, so because we were designing a mode 5 counter with the JK flip-flops, so we first have the JK characteristic, the characteristic table for the JK flip-flop. So when the, here it is, when the inputs 0, 0, 0, the next Qn plus 1 is Qn. When J is 0, K is 1, Qn plus 1 is 0. When J is 1, K is 0, Qn plus 1 is 1. And when J is 1, K is 1, Qn plus 1 is not Qn. Then now we have the excitation table. And remember from what we did last sem, the excitation table is based on the characteristic table. So that is good. So that's our excitation table. I hope we're okay until there. If you have any question, just feel free to interrupt me. Then after that, so a mode 5 counter means it counts from 0 to 4. Mode 5 means it has 5 states, so it counts from 0 to 4. So that's why, so now we have our state table, and it's counting up, and then when it gets to 4, it goes back to 0. So that's why we have, so previous state 0, 0, 0, next state is 1. So then when the previous state is 1, next state is 2, previous state is 2, next state is 3, previous state is 3, next state is 4, previous state is 4, goes back to 0. And then now over here we have the JK flip-flop inputs, which are based on the excitation table. So I hope we're all okay until there. So the next thing you do is to write down the mean terms and the don't care values. Remember, these x's represent don't care values. So for J2, for J2 we had the mean term at 3, don't care value at 4. K2 we had the mean term at 4, the don't care values 0, 1, 2, 3. And then for the J1 we had mean term at 1, don't care at 2, 3. So I think, yeah, so that's how we did this. K1, so K1 had the mean term at 3, don't care at 0 and 4. Yeah. So now after we listed down the mean terms and the don't care values, came up with the kernel map for all of them. And then what we did, okay, we didn't start with the D, but when you look at D, there was a statement where you treat the unused states as don't care values. So that's actually what we did for E also. So like, because our counter is counting until 4, 5, 6, and 7 are also don't care values in all these cases. So in addition to these don't care values, the ones that we listed for all the J and Ks, 5, 6, and 7 are also don't care values. So from this one, since we had this just one, we grouped these two, got Q1, Q0. Hope you can all see that. Then for K2, we had the one here. Obviously 5, 6, and 7 are don't care values. And then also from what we listed above, I'm so sorry. Okay, so from what we listed above, these were also don't care. Guys. Okay, sorry guys. Okay, so my laptop has hung. Okay. I'm so sorry. um, okay, guys. Just give me a moment. Okay, yeah, no, it's okay. Oh yeah, so okay, Kamara, maybe you can present as I sort this out. Okay, no, it's come back. It's okay. Hiya. So now, because so we had the one, and then we have all of them. And you remember when you have don't care values, if you're grouping ones, you can assume all of them because it's either 1 or 0. So in this case, we had all 8 as 1. So K2 is 1. And then, so you do the same for J1. We had the 1 at 1. And so we grouped these 4. So J1 is Q0. K1 is also Q0 because we grouped these 4 with the 1 here and the 3 don't care values. And then, so we have J0. We had the 1 here. Sorry, we hadn't drawn this one, but we grouped these 4. And so we ended up with not Q2. And then we had K0. We had the ones here, and then we had all the rest were don't care values. So we assumed all of them are 1. So K0 is 1. And then after that, we had the diagram. So we have the 3 flip-flops, as you can see. Okay, it's hanging again. So, okay, yeah. So we have the 3 flip-flops, as you can see. Yeah, I think we'll send that diagram to the group so that you can see nicely. Because yeah, so that's it from me. I think Kamara can present the other one. Oh, are there any questions? Okay.
Noel has a question.
Mike, asked you to explain exactly what you mean by don't care values.
Oh, sorry, guy, I wasn't checking. Oh, sorry, I didn't check the chat. Don't care values means, okay, let me just show you. I think it's this one higher. So you see when, okay, so you see we have this characteristic table, yeah? So let's take an example of this of here, because here we have a don't care value. So when the previous state is 0 and the next state is 0, when you come back to the characteristic table, so you look at here, so next state. So here in the characteristic table, look at the next state. So next state being a 0 can
Wakabi,
be,
we can see your
yeah?
screen. We can see your screen.
Oh, guy. Oh,
Yeah, yeah.
sorry. Oh, wait, I stopped presenting and forgot. Sorry. Can you guys see now?
No, not yet.
Not yet.
Okay.
Yeah, now it's coming. Imekuja.
Okay. Okay, so you, okay, so let me start again. So we have the characteristic table here and the excitation table here. So I'm going to look at the first row here because we have a don't care value higher. So now we have previous state is 0, next state is 0. When you come to the characteristic table, so we're going to be looking at this column here. So Qn plus 1 is next state, yani higher. So when you have next state as 0, so this means it doesn't matter the previous state, so we have the next state as 0. It means J, the input J is 0 and K is 1. So we have that. Also, if you look at this, previous state is the same as next state. When you come back to the characteristic table, it's the same. It's like next state being Qn. You remember previous state is Qn, next state is Qn plus 1. And in this case here, we have next state as Qn, meaning previous state is equals to next state. So it means the input of J is 0 and the input of K is 0. So we have these two. It can either be these two. It can either be J is 0 while K is 0, or J is 0 while K is 1. And because K can either be 0 or 1 when J is 0 to come up with previous state being 0, next state being 0, then we say K is a don't care value. Yani it can either be 0 or 1. Yeah, so answers your question. Michael, does that answer your question? Michael. Okay. Is there any other question? Okay, so
Tamara, you're muted.
Sorry, I didn't know I was muted. Thank you, Andrew. Okay, yeah, so before I continue, I'll try to answer Sean's question. And he was asking why we did, okay, it's question C for those who are joining us now, C1. And he asked why we did the 1024 by 4. Why not use 1024, which means memory locations? And okay, if you check the digital electronics book on page 223, I decided to use this illustration. So we have it's a 8x4. Yeah, it's a 8x4 room. And we have the horizontal lines which represent the memory locations, and we have the data output. So in this question, they said it's 1024 by 4 capacity, and by capacity, I'm assuming it means the whole thing. So if we only consider the horizontal lines, what happens to these instances where we could be storing a 1 or a 0? So I believe you have to multiply. So in this case, like it's 8x4. These are 32 locations, and yeah, they could either have zeros or ones stored on them. So I think that's why you should do 1024 by 4 to get the actual capacity of the chip and the number of locations where you can store information. Because I think a bit is either a 0 or a 1. So yeah, I hope that explains. Sean?
That makes sense. Thanks.
Yeah. And then, yeah, so D is just the same logic as then you can be used in E. So I don't know if you want me to go through it or you understood. Should I go through it?
Personally, I understood. So maybe just show the diagram, I guess, to save also on time.
Okay, yeah. So yes, you need your your excitation table, and then we did the same state table where you have your present state, next state, and then your flip-flop inputs. And then we did our kernel maps. So here, the unused states are going to be 12 to 15, because we are only, a mod 12 counter will only count from 0 to 11. So yeah, that's where the don't care states will come in here. And then you'll group them according to your preference. And I learned today, I didn't know. So you cannot use the unused states on their own. You have to either use them with ones or zeros, depending on the table. Yeah, and then, so yeah, you obtain your equations, and then you get your diagram, which we'll send to the group. Yes. And I also have a question. When we were discussing this, we realized that if we're doing this question without reference, the first thing we'd have done is would have solved it like the decade counter we did in class, where we just came up with a circuit for the detector, which would detect the number 12, the binary number 12. And I personally think I would have been correct. So if anyone knows why we have to use this long method to do this question, please share. And yeah, I think I'm done. Is there any question?
question 1 we are done. On to question 2. Was it Gishiru? Gishiru.
Yes, hi. So Fiona will present part of question 2 and then I'll present the other part. So she'll be going fast.
Okay, hi guys.
Hi.
Question two. Okay, so this question 2 is very, very interesting. So the way it is, we can't start from A, B, C, D like that. So we decided to start like from somewhere point where we can understand, then going to the more complex parts. So so design, we're going to start with part 2C. Yes. So I should be presenting now. Okay, let me present my screen. Okay, it's coming. Yes, I hope so. So can you see that? Yes. So yes.
Yes.
Okay. Design a combinational circuit using a ROM. The circuit accepts a 3-bit number and outputs a binary number equal to the square of the input number. So when you read it at first, you think, wait, okay, but then we found a book that is very, very interesting. It had like most of these questions there. It's Digital Design by Morris. So when you start reading from section 7.5, you'll find all the questions there and it will be quite very, very easy. Okay, so for that, design a combinational circuit using a ROM. The circuit accepts a 3-bit number and outputs a binary number equal to the square of the input number. You can see that, yes? Okay.
Yes.
So step 1, you first need to derive the truth table for a combinational circuit. But okay, so like a ROM, a block diagram for how a ROM looks like, it's like that, this thing. So there are k inputs, and then these 2 power k is the word times n, which n is the output. So if there are 3 inputs, it's 2 to power 3 times n outputs, depending on now how many outputs you've been told is required. So this 2 power k thing is a word. Okay, so we've been told the circuit accepts a 3-bit number. Yes, so we need an output which is a square of the input number. So okay, I hope let's tuende pole pole hapa. So there are k bits. If there are k bits, it means there are 2 power k possible min terms. Yes. So if there are k squared bits, it means the number of possible min terms is 2 to power 2k. Because when you say 2 to power k and then that k squared, it means it's equivalent of saying 2 to power 2k. So because this k here up here, it shows the number of bits. It means now here the 2k is also the number of bits. So it means 2k is the number of output lines. Hamjela amamela. I think umela. Yes, great people. Okay. Mumelewa? Okay, good. So if there are k bits.
Mike akona swali.
Mike, yes. Just say your question because I'm sharing the screen. Just ask. Mike.
I think his camera might have an issue. Amesema backup kidogo.
Okay, I'm saying if we have k bits, what does that mean? It means the number of possible min terms, or the number of possible min terms is 2 to the power k. So if we have k squared bits, what does that mean? It means the number of possible min terms is 2 to the power of k, and that k is also to the power, that k is being squared. So that thing for, I don't know what we call it in high school, that thing for simplifying, when it's k power 2 and k is an index, it means you can write 2k or k2 there. Yes? Yes or no? I don't know. Mnanielewa?
Yeah, unaeleweka.
Okay, so now it means the number of output lines we'll need here is 2k. So we've been told the circuit accepts a 3-bit number and outputs which is a square of the input number. So it's a 3-bit number. So our k is 3. So our output, we said output is 2k. So our output will be 2 times 3. So 6 is the number of output lines. Let me call it lines for lack of a better word. So that is what we have, right? So now we said step 1 is to create the truth table for the combinational circuit. So we have, now we are going to write our 3 bits, so 0, 1, 0, 1, 0, 1, like that. So this one is 0, 1, 2, 3, 4, 5, 6, 7, like that, right? So, oops, sorry. So what does that mean? It means we need the square. So we need the square of this, the decimal number here. So see, this is 0. This line here is 0, right? This one for this first min term, yes? Okay, please, someone to just, their audio to be just on so that
Yeah.
Okay. Yeah, I just need someone's audio to be on the whole time. So if this is 0, 0 squared is 0. 1 squared is 1. So this part here, these B's here, they're showing the binary number of this decimal part. Remember, we need 6 output lines. So you're going to write B0, B1, B2, like that, right? Yes?
Yes.
Okay. So, yeah.
Elizabeth has a question, I think.
Okay, Elizabeth, ask. Okay, someone to read it for me. Because if I go back, I'll get confused.
Sorry, there's a problem with the mic. I wasn't saying anything.
Okay, fine. So where are we? So this is a squares. This is this decimal part here. This column showing the decimal 0, 1, 4, 9, 16 is the squares of the min terms of this part of this, the decimal number which represents this input. Sawa. So 0, you write it as that. 1, you write it as that. 4, you write it as that. 9, like that. 16. So you can see the decimal number matches the word, this B0, B up to B5, it matches that. So from this, what can we see? What can we deduce from this truth table? We can see that B1, the whole line, this whole line for B1 is zeros, yes? And we can also see B0, this whole column for B0 is the same as the column for A0, yes? So it means that you can come up with a simpler truth table. So we'll just get rid of B0 and B1 in our truth table, or in other words, the output lines for our ROM will reduce from 6 to 4, because we can just set B1 to 0, and we can set B0, the line connecting B0 to be equal to A0. Okay, let me just show you. Yes, yeah, we note that, but yes. So we actually need, yes, 4 outputs, yes. So it means that our 8x4 ROM itakuwa na 3 input lines and instead of 6 output lines, we'll just set B1 to 0, and we'll set B0 to A0. Yes. So our ROM truth table will be looking like that. So when they were asking the combinational circuit, we thought this one looked too simple for Professor Mwangi. So we decided, let's just draw how it actually looks like. I'm sorry, my lines are very crooked, but please just bear with me. Yes, just bear with me and just you'll draw straight lines. Okay, so in a ROM, what happens in a ROM? In a ROM, there's a decoder and there are OR gates. Is it OR gates or AND gates? OR gates, OR gates, yes, OR gates. That's how a ROM usually works. There's a please, I don't know if it's like this. It's a fixed decoder and a programmable or array, something like that. But I'll confirm that. But it's made up of decoders and OR gates. So we're inside this ROM. This thing here is just very, 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 very general. This thing. But inside we have what now the decoders, a decoder and OR gates. So this decoder, because it's we said it has 3 inputs and it has 6 outputs. For what initially, I just want to take you through the thought process of how you know which decoder this is. So because it's an 8x6 ROM, when it goes to the decoder, it will have 3 inputs into the decoder and 8 outputs. Yes, and these 8 outputs will go to before it became 8x4, it would initially go to to 6 OR gates. Because how many number of output lines do we need? We need 6. So we'll need 6 OR gates. Yes?
Yeah.
Yes. So here I removed the other 2 because we saw from the truth table up here they were redundant. It's much better if we get rid of these and set them to the respectable values. So yes. So yes. Is there anyone with a question? So here B1 is set to 0 and B0 goes to here to A0. Yes, so this is how the combinational circuit looks like. Okay, so this crosses, for those, a cross shows a temporary connection from what we read, and then the dot shows it's permanent. So here it means it connects with this one, the E line yote, E ya B5, ukiangalia E line ya B5, okay, this is 0, 1, 2, 3, 4, 5, 6, 7. So it means 7 and 6 have highs, and these others are lows. Let's look at if that is true from our needs. So you see 7 and 6 is high, and the rest are lows. You get? As in, that is if you've not been given, like, if you've been given a circuit and you need to obtain the truth table from a circuit, that's how you come up with it. Sawa. Okay, so I think I'm done. So I think Gisheru can.
Fiona, I have a question.
Yes.
Can you go back to your diagram? You said the crosses mean temporary connections, yes, and dots mean permanent ones.
Yes.
So would it be wrong to use the dots in this particular one, because
the dots in the connections inside? Okay, are you asking because of these dots I have here?
No, because of like okay, on your table, like the 7th value, I think it's 7. It has 1 here, like
yeah.
Yes, it's 1 1 0 0 0 1. That's what That's what you want. So
Yes.
like if you put the dot, is it like, would it be wrong?
Instead of crosses.
Or it doesn't really matter?
Okay, I don't think it really matters. Don't to say it matters or not, but let me just show you the part for the crosses. Is it showing the PDF now?
Yeah.
Yeah.
Is the cross part? Just
the 4. I've seen it. I think I saw it. The 4. Yeah, scroll down a bit. And again.
Oh yeah. So yes, thank you. You saw it. I'm not supposed to see it, but you saw it well. The programmable intersection between two lines is sometimes called a cross point. So yes, and from the different places we've been reading, they always just call it. You only just put a cross. For gigs, that's how they put their interconnections. So I think to be safe, just use an X. The 4 ones in the words are marked with an X to denote. Yeah, are you seeing this part?
Yeah.
The 4 ones in the word, okay, they're just referring to something. Are marked with an X to denote a temporary connection in place of a dot used for a permanent connection in logic diagrams. Okay, does that make sense? Yep. Is it answering or creating more questions?
Can I try an answer?
Yes, thank you.
Kamara, the reason why I think that in this question, for those particular diagrams, I think you should put crosses and not dots, because as you see in the sentence, terminates with in logical diagrams. Now you see in all of those. Okay, let me also present. Let me also present my screen so that I can use one of those in Ini's examples, those diagrams. I don't know. Is my screen visible?
Yes.
Okay, so let me just zoom this out. For example, here, if you look here in such a diagram, you see all these things that have been described as cross points, all these places where these lines intersect.
Okay. I can't see your screen.
We can't see my screen. Who else can?
It's coming. It's coming.
Oh.
You can see it.
Can you see it now?
Yeah.
Kamara.
She's left the meeting.
Yeah, she's left. Oh.
Let's give her some time to join. But just continue your part, then remember to go back and explain.
I had a question before you continue. Fiona,
yes,
where you use the B0, no, B1, you said it will be 0 all the time. In the diagram, is it okay to put B1's input as 0, or should the diagram have that ground sign?
Good question. Over to you, Kishefu. I'm not sure. That's why I'm passing it over. Okay, I'm seeing it has a 0 in the book. So I like in the book where I extracted this information from. They have
my thinking will be if you put a 0 there, meaning you're dedicating an input which is always 0, but if it's ground, the IC itself has its own ground, so it can be the same circuit.
So we ground B1.
That's what I'd think, unless someone else has a better opinion, maybe an educated one.
What I think is that, okay, yeah, B1 can be grounded, yes, but B1 essentially is not, it's not a part of the IC because, okay, I don't have Fiona's diagram, but if you look at her drawing, you'll see that B1 and B0 are both outside that key box. B1 and B0 are not part of the ROM chip. Because you see, ultimately we have an 8x4 ROM, and B1 and B0 are not a part of that 8x4 ROM. So yeah, okay. I think you can ground it because ground logically is also equal to 0. But if you're going to ground it, you will ground it separately from the ROM itself. And Andrew, I've sent the book to the Telegram group. You can look for it there. I've just sent it. So, okay, so Dan, I hope that answers you. I'm also not sure if it does, but I hope that's satisfactory.
Yeah, I'm cool with that. In case I find anything somewhere else, I'll be sure to share, but I'm okay. Can continue.
Okay, all right. So, since I don't think Kamara is back, is she? No, she's not. So, I think we'll just go on, and I'll take us through part B. Let me just present my screen. Can you see my screen, guys?
Yes. Yes.
Yeah. Also, you keep your mic. So, part B reads, tabulates the table for an 8x4 ROM that implements the Boolean functions below. Considering now, yeah, I didn't do that part. Okay, I'll do it on the fly. Considering now the ROM as memory, specify the memory contents at addresses 1 and 4. So you have A in X, Y, Z, Z is equals to the sum of mean terms 0, 3, 4, and 6. B in X, Y, Z is equals to the sum of mean terms 0, 1, 3, 7. C in X, Y, Z is equal to the sum of mean terms 1 and 5. And D in X, Y, Z is equal to the sum of mean terms 0, 1, 4, 5, and 7. So, yeah. Can you see this part B 8x4? Can you see that?
Yes.
So in our question, we've been given an 8x4 ROM, and the naming format for ROM, as has been explained before, is 2 to the power k by n ROM. And now inside the ROM structure, again, it's made up of a k by 2k binary decoder and n OR gates, which will now give us our n outputs. So our inputs represented by k are x, y, and z, and our outputs n are now what the question has termed as A, B, C, and D. We're good until that?
Yeah.
Okay. So the diagram is just for demonstrations purposes. So if we were to draw our ROM chip, we would have here our k by 2 power k binary decoder, which is now 3 by 8, and our n OR gates representing n outputs. In this case, we have 4 outputs, A, B, C, and D. So from our knowledge from 3.1, we know the binary decoder as a mean term generator. So it takes X, Y, Z, Z, and gives us the meantime, all the meantime that can be got from the binary combination of X, Y, and Z. So 0, 1, 2, 3, 4, 5, 6, and 7. So since all these OR gates, they all have 9 input lines. 9. They have 8 from 0 to 7, and then this extra one that will always go to ground. Those will be grounded because we know from the axioms of Boolean algebra that A or 0 will always give A. So if you were to take A in X, Y, Z as the sum of min terms 0, 3, 4, and 6, all we'll need to do is we need to make our connections at 0, 3, 4, and 6. You can see that?
Yeah.
Okay. So, and then B from the question is also the sum of min terms 0, 1, 3, and 7. So we'll just make our links at 0, 1, 3, and 7. The connection for C is 1 and 5. So we'll make our connections 1 and 5. And for D, they're at 0, 1, 4, 5, and 7. So we'll make our connections in 0, 1, 4, 5, and 7. And then now eventually for our table, here we have our inputs, X, Y, and Z. And now this mesh, this array over here is what will be represented by our outputs. So we go down to the table. So if you have X, Y, Z, 0, 0, 0, it's like saying, giving the name of the address 0, because the min term of 0, 0, 0 is 0. So if we go to address 0 and we read what has been stored in address 0 here, which is now manifested as these X's, where these crosses, where each cross represents a 1 and lack thereof represents a 0. So the data that is stored in address 0 would be 1, 1, 0, 1. 1, 1, 0, 1. You can see that.
Yes.
Okay, similarly for address 1, we'll have 0, 1, 1, 1. For address 2, we'll have all zeros. For address 3, we'll have 1, 1, 0, 0. For address 4, we'll have 1, 0, 0, 1. Address 5, we'll have 0, 0, 1, 1. Address 6, we'll have 1, 0, 0, 0. And address 7, we'll have 0, 1, 0, 1. So that's just what I've put down over here. So this essentially is the programming table for the ROM, because this is exactly how you're going to burn these things, these addresses, so that you can store this information that you have. So yeah, what the question went on to ask, considering now the RAM as memory, specify the memory contents at addresses 1 and 4. So addresses 1 and 4, which is 001 and 100. So in address 1, we have this 0111 as its content, and at address 4, we'll have 1001 as its contents. I just didn't put that down. I forgot to read that part. So we're good there. You get?
Yeah, gettable.
So has Kamara come back?
She has.
She has. Okay. So Kamara, let me just keep presenting. Kamara, Uko, can you hear me? Hello. Oh, okay, she can hear me. So for the question that she was asking, let me just use this example. Can you see my screen, Kamara? No. And I can't read the messages. I can't read the chat unless I go back to the.
She said yes.
Oh, she said yes. Okay, so I think you should use crosses and not the dots, because the crosses and dots are representations in logical diagrams. All of these cross points, these 1, 2, 3, 4, 5, 6, 8, all of these cross points are physically, they're just fuses. They're fuses that connect these lines, these horizontal lines, to these vertical lines. So anywhere where there's a cross, it means the fuse has been left intact. Anywhere where there's no cross, it means that fuse has been blown, which means that here there's an open circuit, open terminal. Like this connection here has been severed. The connection between line 0, address 0, and this OR gate for A6 has been severed by the blowing of the fuse. So now, if I happen to put a dot, say if here I removed the cross and I put a dot, that would mean that no matter what, this connection between address 0 and this OR gate for A7, this connection cannot be severed. It will always remain intact. And that's not true, because this is a fuse as well. It's just that according to our design, this fuse has been left intact, but it can be broken. It's just that we don't want it to be broken. You can compare it to, like, in this diagram of mine here, I've put dots here, here, and here. There are 3 dots over here, showing that this connection between this OR gate and this ground, and this OR gate and this ground, and this OR gate and this ground, and this OR gate and this ground, this one will always be there, no matter what, unless I literally break this whole thing into tiny pieces. This connection will never change. But these ones with the X's, they can change because of fuses. It's just that since you want our ROM to store certain information, we leave them intact. Does that answer your question? Okay, so you're welcome. Okay, over to Fiona.
Okay, so now we are going to question A. So, okay, once it's on, just someone give me a heads up that it's on. So, question A, what was it asking? Derive the ROM programming table for the combination circuit that squares a 4-bit number. Minimize the number of product terms. So you can clearly say CA. You guys can see, right? Yes?
Yeah, your screen is presenting.
Okay, so question A and C are quite similar. What questions they are asking for the same things, but it's just the same process, really. This one is combinational circuit for a 3-bit number, square of the input number. And this one is a 4-bit number, square of the, yes. So, number of product terms. So this one is slightly longer, but we are not doing we're just drawing a table and we're just doing K-maps. because we need the least number of product terms. So, okay, please bear with me. and my it should work, but yes, muhimu ni content. So, we need 4 bits as the input, yes? So we have W, X, Y, Z as our 4 bits. So now we know if K is the number, if it's 4 bits, it squares the squares that. So it means that this is going to be 2K. The output is going to be 2K. See, we understood that from what I explained in C, yes? So so it's generally the same thing. I don't want to keep repeating. I just want us to go to the K-map, but then this is just an extension. That this part is the from inputs, then this is the output. I hope you can see the cursor. I don't know if you can. So what do you notice again? We notice that B1, everything is 0. And we also notice that B0, everything is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, like that. So what do? We get rid of B1, B0, and B1. So our reduced table is going to have B2 to B7. So it's going to look like this. Yes, this is the solutions book. I'm going to send it to you. It just shows the solutions really, and it doesn't show you the process. It just shows you that. Okay, so yes, I'm going to send the page and everything. Please don't look at this part. This 4x8 thing is wrong. I think it's very, very wrong. So when you reduce it, you only have B2 to B7. Okay, thought here they are not going to have B0 and B1. I don't know why it's not reduced here. But I think the 6th edition doesn't have this part. This part is not supposed to be here. I thought that was where I was moving. Yeah, okay, fine. So, yes, and then now you go to the K-map. So why are we going to the K-map? Because we need the minimized number of product terms. Like you know what I mean, like, you know how a Boolean expression is, a function is, and then it has so many terms, and we need to reduce it. That's what this question is asking. Like from the truth table, we now come and take B7, and we see it's in 12, 13, 14, 15. 12, 13, 14, 15. Then we circle that, we find its WX. You guys remember how to do K-maps. So initially what happened here, I would have presented these, we'll not be doing these things again. But then as you can see, please note in the book, in this solution book, this part is YZ and WX. So it means this is this is the LSB and this is the MSB. But how we've been taught, MSB is here and LSB is down here. So it's supposed to be WX and YZ. So that's why I drew it again. So for those who cannot understand, who are very confused about how those K-maps are looking. Tuko salama. So this is easy. Yes? Yes?
Tuko salama.
Okay, great. So K-map. The K-map for B7. Remember, each Nini is its own different function. I don't know if Gisha mentioned that, but you see this whole thing, it's its whole different function, different function, different function, different function, like that, like that, like that. It's not all the same. Yes. So B7 WX, because yes. Okay. See you guys. Do I need to explain K-maps really? So that's for B7. This is for B6, B5, B4, B3, and B2. So you just come and just write B2, B3, B4, B5, B6, B7. And that's how you do part A. Any question? Have I gone so fast with that? Or is it? Hello, guys.
Hello. Hello.
Yes.
Hi.
Hi.
Yeah, I think uko sawa.
Yes. Okay. I just didn't see the point of going through the whole process of drawing a table like one by one, and it's the same thing as question C, only that this one you're drawing came out and then you just showing the reduced product, minimized number of product sums. But you don't show B0 and B1. In the product terms. Sawa sawa?
Sawa sawa.
Okay. Kishero, over to you.
Thanks. Yeah. So are we going to let's see. Is my screen? Can you all see my screen?
Yes.
Okay. So part D. Part D reads, draws the PLA circuit that implements the following functions. F1 is equals to not AB. F1 is equals to not AB or A not C or not A, B, not C. And F2 is equals to AC or AB or BC, all of that's complemented. So first, there was something that Fiona had said earlier concerning this little diagrammatic representation. So the structure of a PROM is a combination of a fixed AND array, which is now your binary decoder, and a programmable OR array, which was a part which had the X's that you could blow depending on what you want. Now, programmable array logic is where you have a programmable AND array, and then you have a fixed OR array. Now, for the PLA, which is what we'll be going through in this question, both the AND array and the OR array are programmable, because all of these things, they implement SOP using invert and OR implementation. So yeah, this is just something that she had mentioned earlier, and I just wanted to clarify. So yeah.
Thank you.
So this is just what I've just said. So now here we go to the table, and before we go here, let me just look for some piece of information. Is it? I have no idea where it is. It's something that needs to be here. Yeah, this highlighted part for n inputs, k product terms, and m outputs. The internal logic of the PLA consists of n buffer inverter gates, k AND gates, and m OR gates, and m XOR gates. There are 2n by k connections between the inputs and the AND array, and k by m connections between the AND and OR arrays. and M connections associated with the XOR gates. So here we have N inputs. Here we can see that we have 3 inputs, A, B, C. A, B, and C. Now, the number of product terms, which is what we call K, is what I've just, it's 1, 2, 3, 4, 5, 6. Because we have 6 different product terms over here. Okay, and before I continue, these product terms, also when you're doing the PLA implementation, they should have the minimum number of distinct product terms, because this PLA thing is very, it's called density something. It uses kidogo gates. It's good to use as few gates as possible. So we have N inputs, K, we have 3 inputs, we have 6 product terms. So we'll have N buffer inverter gates, K AND gates, and M OR gates, and M XOR gates. I'll get to that. Let me just go through this table, and then I'll get to that part. So now, in this table, I've written down all the inputs, the numbers. Now here, the part for inputs, I'll go through the legend first. So where I've put a 1 in the table, it means that there's a connection with the true input. What I mean is that if you have A and B, you'll have an A input and you'll have a not A input. So when I say true input, I mean like the A input. And then 0 is a connection with the complementary input. Now that would be the not A input. And when I've put a dash, means that there is no connection. The fuse has been blown, which means there's no electrical connection there. So C here means that eventually the output will be this C and T are for the XOR part, which we will get to. So C means that the output at the XOR gate will be complementary to the input, but T, which stands for true, will just give the true output the way it came from the OR gates. So yeah, axioms to note: X XORed with 0 will just give you X. X XORed with 1 will give you not X. X and 1 will give you X, and X and 0 will also give you X. Are there any questions until there? Any questions? Question. Okay. No questions. Can you still hear me? Have I lagged out? Can you still hear me?
Yes.
Can you see my screen?
Yes.
Okay. So now here, this whole thing is now the circuit, the PLA circuit that will be used. So here we have N inputs, which means that we will have N buffer inverter combinations. And I hope everyone knows what this symbol means. This symbol. Yep. So since we have 3 inputs, we'll have 3 buffer inverter combinations. And since we have 6 product terms, we will have 6 AND gates. That's K AND gates, M OR gates, and M. And since we have M outputs, we will have since we have 2 outputs, we will have 2 OR gates, and we will also have 2 XOR gates. We'll have 2 MPK connections and mini KBM connections. That's not important. So now for the PLA, how you will put these crosses is all of it is in this table. So here, if for instance we're going to take AB, we're gonna keep this. We're gonna keep the fuse of A intact and the fuse of B intact, and then we will blow all the others. We will blow all the others. C will be blown. Here, C will be blown, and not A, not B, not C they're pretty much irrelevant. So, and for not AB, we will connect not A and B, and the others will be blown. Because here in the table, this here is now like what I mean when I say 0 and 1. This not A has been denoted as a 0 on the table, which means that I'm going to keep the fuse from the complementary equivalent of A intact, and I'll get rid of all the others. So this is not AB going through the AND gate here. This will be AC, A not C, BC, and not A, B, not C. So yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So from our Boolean expression, if we go through F1 first, we have not A, B, or A not C, or not A, B, not C. So we will keep the fuse for A not B intact, the fuse for not AB intact. We'll keep the fuse for A not C intact, and the fuse for not A, B, not C intact, and we'll blow the others. And then the same thing here. According to this expression, we'll have AC or AB or BC. So here we have AB, we have AC, we have BC. Those will be kept intact, the others will be blown. And all of these will go into our OR gates down here. And then and this is the part where these axioms will apply these ones for XOR. So since as you can see, F1 is not complemented at the XOR, it is just given as is. You have made a mistake. This should have been T, and this should have been C. I'm sorry, I will correct that. With this thing. Yeah. So this here, this should have been, never mind. Use this one instead. This should have been T. This. Okay, you know what? Just imagine. This should have been T, and this should have been C. I'm sorry. I don't have a mouse. So, so here I probably made a mistake here then. Also, I will correct this before I send it to the group. So if you have X XORed with 0, we're going to just get X as a result. And since F1 is one that's not being complemented, the line that will give us F1 will be XORed with 0. So here, F1 here will be XORed with 0 over here, not 1. It will be XORed with 0 over here. And since the line for F2 is what will be complemented eventually, we will XOR this, we will XOR F2's line with 1 to get not F2. So here F2 will be connected here at 1, not at 0, to be connected at 1. Then eventually you'll get F1 and F2. Yeah. We good. Any questions? Yeah, I'm done. That's it with part D. Are there any questions? Okay, I'll assume there are no questions, and that's it for part 2. Whoever is next can take over.
Okay, thanks, Gisheru. Hi, guys. Nigel, Stephanie, and I were presenting part 3, question 3. But, oh. Mnaweza nisikia sasa? Okay, so I was saying Nigel, Stephanie, and I will be presenting part 3, and I will tackle part 3A. So while I'm going on, please feel free to tell me if you can't hear me or if you need any clarification. But first of all, I'll present my screen. Mnaweza icheki? Okay, so question 3A says, give the circuit over Ttl Nand Gate and explain its operation in brief. Yeah, so I thought perhaps the best way to know the operation of a Ttl Nand Gate is by going through a question. So there's a question in Professor Mwangi's book, page 64 and 65. It's not actually a question, but there's a sample that he was using to explain. So I'm going to use the same. And yeah, just hold on a second. I hope you guys can still see my screen. Someone please.
Yes.
Okay, so on the left here, over here, is an image of what a Ttl Nand Gate looks like. I believe all of us are familiar to it. It has two emitters, and then the base and the collector have been put together for the two transistors. It's two transistors in one. So T1 consists of two transistors in one, double emitter, and then the bases and the collectors have been put together. So this is the diagram of the Ttl Nand Gate, but down here is the same diagram but broken down in terms of its diodes. So the emitter has the transistor has two emitters. I have represented the emitters using two diodes. And then the collector of T1 has also been presented as a diode. Okay, so just a few things that I thought were noteworthy before we tackle the question. Diodes, including the junctions between transistors, have a drop of 0.7 volts. These are things that we already know, but I just thought they were important in explaining the question. So a Ttl Nand Gate has 3 stages. The first stage is called the multiple emitter transistor, as you can see it on the left. Has diode D1, diode D2, which represents the two emitters. So it's a multiple emitter transistor. The middle section that has a resistor RC2 and transistor T2 is the second stage. It's called the phase splitter. Now, something interesting about the phase splitter is it provides voltage signals of opposite polarity. So the branch just below RC2 that goes to B4 provides an opposite polarity to the branch after transistor T2. So that means that T4 and T3 will always operate oppositely. And the third stage, this one here, which is the last stage, it's called an emitter follower. Whenever transistor T4 is on, transistor T3 will be off, and vice versa. So T4 is termed a pull-up transistor, and T3 is termed the pull-down resistor, as we will see. Our output is going to be at Y, and T4 is going to play the role of giving us a logic high, and T3 is going to play the role of giving us logic low, hence pull up and pull down. So then let's look at a first case where both inputs A and B are held at 5 volts. We know how a NAND gate works. When we have, it only gives a low output. Let's see. Yeah, it only gives a low output when both inputs are high. For the rest of the inputs, we have lows. So then if we have A at 5 volts and B at 5 volts, then diode D1 and D2 will not conduct. Since that will mean B1, the voltage at B1 has to be at 5 volts, 5.7 volts. So that if there's a drop at A, it drops 0.7 and then it's 5, and then at B as well. So since B1 cannot be at 5.7 volts because that is going to be higher than the supply, diodes D1 and D2 are not going to conduct. So then the voltage at B1 is going to be given by this other path through D3, T2, and T3. And since the voltage is 5 volts, we have enough voltage to take T2 and T3 into saturation. Because there's going to be a very small drop at this resistor. So assuming at the voltage at B1 is approximately 5 volts, it's going to drop enough here and drop enough here to take it to saturation, and drop enough here to take it to saturation. So then to calculate the voltage at B1, we're going to take the drop at diode D3, and then we will say that T2 is in saturation and T3 is in saturation as well. So the voltage at B1 will be 0.7 for the drop at the diode. Remember we said there's a 0.7 drop at the diode, and then VB2, it should be VBE, BE2. This is a mistake. Should be VBE2 at saturation is at 0.75, and VBE3 at saturation is 0.75. So then we figure out that the voltage at VB1 is 2.2. Now we already know the voltage at VB1. We have calculated it through this path here, the path that goes through T2 and T3. So we know the voltage at B1, and the voltage at B1 can help us get the voltage at B4, which is VB4. So let's see, voltage at VB4 should be, remember the voltage here at B4 is going to be dropped here at T2, and the remaining one will be dropped here at T3. So we can calculate the voltage at B4 by taking the drops here and the drop here. So through this channel here that goes to T2, that will be the collector in respective to the emitter. And we know that T2 is at saturation. So VCE2 is 0.2 volts. And then at T3, it's the base with respect to the VBE, with respect to emitter. And T3 is also at saturation. So if we add the two, we get the voltage at B4 to be 0.95 volts. Now, suppose T4, D4, and T3 are active. we know T3 is active, is in saturation, but suppose T4 and D4 are also active, then this voltage at B4 should be able to supply T4 and D4 as well, and the output. Now, if we take the total voltage dropped, assuming that T4 and D4 are active, then the total voltage dropped should be equal to 0.95 volts, because we had already calculated the voltage at B4 to be 0.95 from this other path. So then we get the voltage at VB4. Voltage at VB4 is 0.95, and that should be equal to VBE4, the drop in this transistor 4, plus the drop at D4, the diode, plus the drop at transistor T3, and we already know that transistor T3 is in saturation. Now, since the voltage at B4 is less than that is required to operate transistor T4 and D4, then transistor T4 will be in cutoff. Now, we realize that that voltage at VB4 is 0.95 volts, and for this transistor to be active, it will take 0.7 volts from 0.95 volts. And then we will be left with 0.2 volts, which is supposed to be the drop at this diode. So the drop for a diode is 0.7 volts. So 0.25 volts that is left is not going to be enough to drop at D4. So then this path will be inactive, the path through T4 to diode D4. So then T4 is going to be in cutoff. And that explains why T3 and T4 are opposite, because we realized T3 was in saturation, and we have figured that T4 is in cutoff. And we will see later on that when T3 is active, T4 will be the opposite. When T3 is cut off, T4 will be active. So there's no current flowing through T4, and our output for our first case where A and B are at 5 volts, our output is going to depend on transistor T3. And since our output is tapped at the collector of transistor T3, we know transistor T3 is already in saturation. So our output at Y is going to be the collector current of T3, so VCE3 at saturation, which is 0.2 volts. So that's our first case where A and B are at 5 volts. The output is 0.2 volts. Any questions so far before we go to our case 2? Can you guys still hear me?
Yes.
Yeah.
All right. Any questions, please? Okay, feel free to ask any question even as I go on. So case 2, we have already looked at our first case where both A and B were held at 5 volts. Now in our second case, if either A is 0 volts or B is at 0 volts, then the respective input diode will conduct and the base voltage will be 0.7 volts. Yeah, so if we have a 0.7 volts drop at D1, and either A or B is at is held at 0, then VB1 has to be at 0.7 volts, so that after the drop we have a 0 volt at either A or B, respective with whichever has been set at 0 volts. And if both inputs are also at 0 volts, both diodes will conduct and VB1 will be 0.7 volts. Yeah, if both of them are also held at 0, B1 has to be at 0.7 so that after the drop we get 0 and 0 at A and B. Remember, it's A and B that has been set. It's like A and B are the master. So once A and B are set to 0, or A or B is set to 0, then VB1 has no option than be at 0.7 volts, so that after the drop we have 0 and 0 here. This was just for clarification, the diagram. I had a little problem myself not figuring out why we have 0.7 volts even when both A and B are set at 0, but I figured it's a parallel connection. So assuming you have a line here that is B1, this point, this node, if we say that this line here is held at 0.7 volts, after drop, both lines are going to be at 0. So even when both A and B are set to 0, VB1 will just remain at 0.7 volts and not 1.4 or something. Initially, I had a problem, so I thought it should be 1.4, but I saw it later. So either A or B, or A and B. If both of them are at 0, VB1 is at 0.7 volts. So since VB1 is at 0.7, it's not able to drive transistor D3, T2, and T3. 0.7 is just enough to drive the diode alone. So if it's going to be shared between all of these, it's not even going to get to a cut-in voltage for the transistors to operate and for the diode to operate. So all this path down here is going to be on cutoff. And remember, if T3 is cut off, then we said T3, T4, they operate oppositely. So if T3 is in cutoff, T4 has to be in saturation, but we will see in a moment. So T4 will now be in conduction and it supplies a current to the load. If the output terminal is open, so we are going to consider two cases. We have figured that T4 is in conduction, but we're going to consider a case where Y is open and where Y has a load. So if Y is open, then T4 and D4 will be in very slight conduction, and IL will be a small leakage current. IL is going to be the current flowing, the small leakage current flowing through T4, D4, and T3. The base emitter voltage, VBE4, that's transistor 4, and the voltage across the diode, VD4, will be in cut-in voltage. So cut-in voltage is cut-in voltage, or it's also known as knee voltage or threshold voltage, is the minimum voltage. Just imagine just to the point where the transistor starts to conduct. So it's almost 0.7, but not quite. And in this question, it was given as 0.6 volts, 65 volts. So the cut-in voltage is the voltage that we're going to use when we consider no load at Y, because there's just a small leakage current. So the small leakage current is just going to be flowing at cut-in voltage. Now, I hope I haven't lost anyone yet. Can you guys still hear me?
Yeah, we're still here. We can hear you.
Okay, so these values here, VC at saturation, as we know, be given. But it's good to know that it's usually just about 0.7, just before you get to 0, a little shy of 0.7 volts. Like in this case, it's 0.65 volts. So just to recap, we are at our case 2. Transistor T4 is in conduction. Transistor T3 is in cutoff. So now VB4 was given as approximately 5 volts. So to get the voltage at the load, it will be approximately the voltage at B4 minus the voltage here, which is the voltage that is going to be dropped here. But remember, it's just going to be the cut-in voltage because the transistor is just conducting. So the cut-in voltage is going to be dropped here for the transistor, and the cut-in voltage is going to be dropped here as well for the diode. So we have been given VB4 as approximately 5 volts because perhaps the drop here is negligible. So VB4 minus 0.65 volts, the cut in here at the transistor, and 0.65 volts, the drop at the diode. So in a case where there's no load at Y, the reading at Y is going to be 3.7 volts. Now let's consider a case where there's the load at Y is being increased. So it means the demand of the current is going to be increased, and so we know that the voltage drop is going to increase because V is equals to IR, Ohm's law. So we expect that as the load increases, then the output at Y is going to reduce. So if IL increases, then T4 and D4 will conduct more heavily, and V at the load is going to decrease further. A large value of IL takes T4 to saturation, and the output voltage V0 is given as, so we have VCC, and if we take this first path, then V0, the voltage at the load, is going to be given by the supply voltage VCC minus the drop at the resistor, which is IL into the resistor minus VCE4 at saturation, because transistor T4, when the load is maximum at Y, transistor T4 is in saturation, and then finally minus the drop at the diode. So whatever we are left with after all these drops, we are going to output at Y. So if we rearrange this, we end up with VCC. Now we have VCC as our subject. It's going to give us this. Also, considering a second path through the base of the transistor T4, then there's going to be a drop here at resistor RC2. So Ib4, which is the current through the resistor RC2, plus VBE4 at saturation. Transistor T4 is at saturation, so the second drop will be through VBE4, and then the third drop will be through the diode, and then finally what we will have at the load. So if you look at these two formulas, we have considered two parts. The first one through the collector of transistor T4, and the second one through the base of transistor T4. Then you realize the last two terms are the same, so we can cancel them out and then compare the remaining ones. So then it means if we compare this remaining term in the first equation to the remaining term in the second equation, they should equate. So yeah, Ib4 RC2 plus VBE4 at saturation is equals to the second path. Another thing that we will always be given is the relationship between Ib4 and Il, which is basically the relationship between the base and the base current and the transistor and the collector current. So Ib4 is equals to Il divided by 1 plus the gain. And this is way, way, way less than Ib4 is always way, way high. If we replace our Ib4 with Il so that we only work with Il, we get this over here. I hope you guys can see the equation. And then if we do the math, we end up with IL as 5.6 milliamperes. Now, we already know the current that is flowing. We now know the current that is flowing through the collector of transistor T4. So we have all the other parameters. So now we can get the discrete value of what our output is going to be. So from the equation that we had earlier, V naught is going to be the voltage at the supply minus all the drops. So VCC minus the drop at the resistor minus the drop at the transistor. Remember, transistor T4 is in saturation, and then minus the drop at the diode D4. So if we do that, we get 3.4 volts. So we have two values for the output when T3 is in cutoff and T4 is conducting. We have 3.4 and 3.7. 3.4 is when the load is maximum, so the drops are high. So whatever we end up with here, remember, whatever we end up at the load is after the drops. So when the current is high, which means the load is high, there's more drop. Then we end up remaining with only 3.4 volts here. But when the load is less, then the current that flows is also less. So there's less drop, and we end up with 3.7. So the output voltage in the circuit depends on loading and varies from 3.4 volts to 3.7 volts. This second case that we were looking at was when both A and B are at 0 volts, or either of them is at 0 volts. So if we look at the table, if we have A and B both held at 0 volts, then we have a high, which ranges from 3.4 volts to 3.7 volts. And we have the same for, wow, this should not have been like this. I just figured it should have been A at 0.7 volts, B at 0.5 volts. We'll still have a high, 0.5 volts for A and 0.0 volts for B should still be a high. And both held at high, we should have a low, which is 0.2 volts. And that's a Ttl Nand Gate. I will make this correction before I send the work to the group. But that's it. Any questions? Questions? Or someone just say something so I know you can hear me.
Hey, hi. We can hear you loud and clear, Modulo.
Okay, thanks. So if there are no questions, then question 3B will be handled by Stephanie. Yeah, and then 3C Nigel, 3D Nigel. Over to Nigel. Over to Stephanie, I mean.
Hai, we uko mbali. Hai, uko mbali kwa chumo.
Mnanisikia poa?
Say it's better.
Okay. Okay. So to be honest, I think I got confused. I thought I was doing A in my head. I was doing A. Lakini it's okay. I'll do B. I think
Hello?
can you see my screen?
Hello? Fiona?
Yes,
I don't know if
yes,
you can hear me.
yes,
Hello?
yes.
Uh, tunaweza pata WhatsApp dakika moja?
Ah,
Find me on WhatsApp.
okay.
Niendelee.
Endelea Steph.
Mnanisikia vizuri?
Tunakusikia enough.
Okay. So Sipo very well prepared for B. I got na handle A. In my head, A ilikuwa B, so sorry, I was confused. Lakini this is what I was able to gather. I'm not sure how exactly we were supposed to present this answer. So briefly discuss the various IC logic families and kuna logic families kadhaa. I think I noted them down. There are so many, and some are fabricated based on BJT, and there's the other category are MOS transistors. So I noted them down. It's not really in a way mtu angepresent kwa exam, lakini I think you'll find a way around. So some things I didn't write down. So if I mention something during passing, please forgive me. There are some this uses what you like a diode, resistor, diode, transistor. All these on the left are based on BJT, and there are another category, PMOS and NMOS, CMOS by MOS are based on MOS. So there's at that point, the type of transistor that is used in that specific logic family. And these examples, though you can see the ones that have been obsolete, the ones that we are currently using are the ones that so there's that. I narrowed down to Ttl, MOS, and ECL. I didn't have exact values for ECL. I was using this book. I also didn't mention exact values for the input levels, the current thinking, and so I don't know if actually all this is supposed to be mentioned during exams to get the 5 marks because it's a 5 marks question. So I think you just do discussions based on these characteristics. So in comparison, first thing to note is TTL has a lower noise margin compared to MOS. The noise margin in ECL is not included, but you can do the comparison on noise margin for TTL and MOS. Sorry, TTL I used only the standard TTL, and for MOS for me I did the CMOS one. Okay, so there's a noise margin that you can talk about being lower than for TTL being lower than the MOS one. Fan out. I don't know if I hope we all remember the definitions for for all this? Do I need to explain maybe? Am I sawa? I think that tunakumbuka no imagine fan out, propagation delay, what they are. It's okay then. I can continue. Ni sawa? Nasikika?
Yes.
Okay. So the fan out is basically the number of inputs that can be driven from the output of a gate. And in comparison, you can see TTL does better than the MOS family. So TTL can drive a higher number of inputs from the output, the fan out being 10 for TTL and for MOS being 4. And for ECL has a very high fan out value for it mentioned. And next, regarding the propagation delay delay of the ECL family is the fastest, being 0.79 nanoseconds. I don't have the best handwriting. Sorry. So the next being the CMOS. CMOS has the next best speed, and then the final one is the TTL. Regarding the propagation delay, the time it takes to change states from low to high. Concerning the power dissipated by what's it called? The CMOS family is actually actually very low. For the CMOS family, it's kidogo. I didn't write it, but it's kidogo. And power dissipated by ECL is very high. There is this ratio where there's this trade-off, propagation delay and power dissipation. So the faster you are, and the more power you get to use. So ECL has the fastest propagation delay at the expense of high power dissipation. And TTL has a very low rather it is slow, lakini power dissipation acceptable. It's at 10 megawatts for standard. So as they say, Sikwan may prepare sana. So I've mentioned so many things in passing. I hope Mezandika. I don't think we're supposed to present all these tabulated values, the input level and output. Otherwise, it would be cramming. So as to answer the question, discuss the various isolated families. So I think we just present the characteristics, comparing the different logic families. That's how I would approach the question. If anybody has a different suggestion, any other questions or clarifications, then tell me now. Because I believe I have finished.
Thank you, Steph.
Okay.
Does anyone have a question? Okay, Steph, unmute kidogo ama kidogo. So what would I want? Oh, okay, guys. As you can see, please just look at the time. It's 11:30. I don't know. Is it Nigel who is supposed to be going next? Nigel, is it you who's going next? Hello? Yes?
It's supposed to be me.
Oh, so, okay. Unaona wakati ni saa ngapi? It's 11:30.
Yeah, I know concentration span ya magari zimepotea.
So, So I don't know what you guys, as in we don't want it to go 3 hours. Because by the time you're done, and then by the time Kinalis have done question 4, I think we'll be talking about 1 o'clock in the morning at this rate. I didn't know digital, like, imekuwa very like this, like we have to explain so much. But I don't know what you guys think, because Friday is a holiday. We can choose to do. Nigel, are you okay with presenting on Friday?
Maybe I'll go with whatever the guys say. So
And I can at least just tell us if you're okay presenting on Friday. And then
Friday at night or a different day, like a different time. Sorry.
we can okay, you know, also Friday is a holiday, so I don't know what you guys think.
Oh,
And
so
now,
we meet during the day. You want us to meet during the day to finish up on digital?
during the day might be tricky because for Muslims here who are feasting, who are slaughtering things.
No, I'm just asking, as you say Friday, do you mean like whatever was supposed to be on Friday will be pushed and we'll just continue with digital? I'm gonna manage tukianza tuanze na digital and then we do whatever you need to are meant to do on Friday as well. Like I'm just clarifying.
Oh, okay. I don't know what guys think. It's not just me personally, but I'm thinking we can either you guys be sacrificed and say that we can just meet tomorrow and just finish this together. Just let's wait first and listen. Tomorrow is Thursday.
yes.
No, okay. Okay, fine. I don't think. Okay, maybe. Okay, we can meet tomorrow on Thursday at 9.
Me and May for the opinion.
Okay, so okay. Oh, join again, Joseph. Sorry, I'm not seeing the link. I don't know why the admit thing. But okay. Sawa. I'm thinking. Okay, fine. We can try and meet on Friday. We do the remaining questions. Then I don't know. Do you guys? And then we choose because we are taking digital to Friday. That means you have to do ECT on Monday. Okay, Joseph, I cannot see the link for you to. I can't see you're trying to join, and I can't see the. Let me just send it. Okay, so I don't know how to help you, Joseph. I can't see the link. Hello, Joseph. How is he typing? And okay, I'm very confused, but this woman is confusing. Okay, what was I saying?
Which one?
Huh?
Which woman is confusing you?
I've not said woman. I've said man. Usually, you people. I'm saying Joseph is confusing me. He's talking. He's here, but then he's not here. I'm sorry.
Shundiga's Joseph.
Huh?
Shundiga's Joseph.
Okay.
I think you're trying to join on another device.
Okay, let me just. Okay, so you guys, what do you think about what I've said as I'm trying to sort Joseph out?
Friday sounds okay.
And then we do and then we take a break because I'm very sure. Have all of you gone through all the question papers?
Hapana. Sijani.
No.
Yeah, so I think we need to take our time now, like for the remaining days. We don't take any more questions. We just try as much as possible. We go through the questions that you think that all those papers and all those videos, so that on Monday we start on bang, clean slate again, so that you don't have like workload. You get. Mnafikiriaje? Just talk to me.
Until we do those remaining questions from now till Sunday, Amma.
Hello? Hello?
What do you
Fiona.
mean?
Okay.
Hello?
No. Yes,
Yes.
yes.
Eh, we haijakuwa rahisi, haijakuwa rahisi. What's going on here?
So, okay. Let me say again what is going on. Then I go to you, Kamara. Andrew, we can see your face. You're glowing, and that's nice. We are saying that we want to, because Nigel and I had to stop Nigel's group, Steph's group, Mbalo's group. I had to stop them midway so that we could all just take a break and rest because we are 30 minutes past the time. So I'm suggesting, everyone is allowed to make suggestions, but I'm suggesting meet on Friday. Nigel and Nigel's group and Akina Sean, they do their part, and then when they do their part, we don't do anything else. Okay, we just choose the questions for ECT for Monday. So between now and Monday, between Wednesday and Monday, those are like some few good days so that we can recover on the analog paper, EMF paper, and the digital paper. Like we go through the questions that, like personally, I've not had enough time to finish those papers, all of them, mara moja. So I personally feel like I need the time to now go through those papers well, so that I can ask, I can understand before we move on to ECT. So, and then Amara had a question, and then that's the point you came into the meeting.
Really?
Yes.
Okay, now I'm up to speed.
Tamara?
It's okay. She addressed the question I had.
Okay. So the other guys kubaliana ama hawanakubaliana?
Tunakubali.
Hi Andrew.
Okay.
Hi Elizabeth.
But me have a question.
The other guys?
Fiona, ameenda wapi?
I'm here.
Okay.
Okay, so Kamara, what was okay? I think Kamara was saying something. Then
It's okay. You addressed the question when you were briefing Joseph.
Okay. Okay, so I found you guys talking. What were your suggestions?
Okay. So we're going to pick the next things on Friday.
Yeah.
Yes, I think, gosh, we are tired, or I'm tired.
Clarifying.
I don't know. If you guys have the energy, fine. I don't mind. If you have the energy to select ECT questions that we can have time to look at them right now.
Let's
I don't have.
let's not do that tonight.
That's the only thing Sean has said this whole time.
Okay, just against it. Sean, you want us to select it now?
No, Sean doesn't have energy. He wants a break.
Oh, okay. Oh, okay. So we are all agreeing that we need the break, yes? Up to Friday.
Yeah.
Yes.
Up to Monday.
Okay. Here's something in Nimekwekini. I've been thinking about how we're doing it, and yeah. One is I like the strategy ya kuchukua paper na kuifanya ya kutake a whole paper and we disassemble it all through in one session, because it somewhat gives us the idea that we are doing a paper, in any one course we choose to tackle that week. However, I find it raises questions of efficiency as to how good we are doing it. And yeah, because I'm thinking about it and I'm like, so for what we did on Monday and what we did today, because of the pace we did it, I'm going to have to find time again to still go back through it. And if we are to continue with the same pace, that means I have this backlog rather from the sessions I've already had. And then of course, because I have to stay up to date with what's coming next, I also have to try and go ahead. So I don't know, maybe we shouldn't think about it as papers, as in we shouldn't think about it as papers. We should more or less look at it as a pool of questions and grabbing the concept. Just look at them as one big dossier, and we are trying to get questions that are packed with stuff that we can learn. And because paper na imagine ile ndio nikwe niseme niko comfortable enough with what we've done this week. I'm thinking the stuff I have to go through is a lot, and since ndo tumeanza kwanza, I feel like we are almost about to shoot ourselves in the leg. So I don't know.
I think that's what Fiona was suggesting, where she said that we can have some sort of a break till Monday, so that we can have time to go through what we've already done. But to add to it, maybe instead of doing 3 units throughout the week, maybe we can do Monday and Wednesday. Then towards Friday, people can do the 2 papers, revise, and any question that comes up, maybe go through it on the Friday session, to sum up the week, maybe going forward. That is.
Yeah, that sounds nice. That sounds really nice.
The 2 units per week also looks much more it looks, I feel it's much better. And I think I like what you're suggesting, Travis.
I also have a suggestion. Instead of it being Monday and Wednesday, why not Monday and Thursday, to give us enough time to go through the paper we've done on Monday and to also prepare for the one to discuss. Because if we do Monday and Wednesday and then come and discuss on Friday what we don't understand, it's kind of the same thing.
Wait. You're saying it on Monday and Thursday, then we discuss on?
No, like the way you're saying, Travis suggested we do Monday and Wednesday, and then on Friday, or towards the end of the week, we meet to go through what we don't understand. I feel like there should be maybe 2 days. It should be at least 2 days between the discussion, so that someone can have time to go through what we've discussed on, let's say, Monday. And then if you're meeting on Thursday, I'll also have time to prepare for Thursdays.
Then
now, I don't know now which day we can meet to go through. But I don't see why we should. Okay, I don't know. But what's the hurry?
Yeah, I agree with that. The for you to be spaced out. Yeah, I agree with both of you. You guys are doing good with opinions. So yes, I agree with what you're saying, Kamara. The difference between the days should be adequate enough for you to go through the last paper and for you to prepare for the next paper.
What if see, the Friday is sort of like going through whatever was not understood, like mostly a brief session. Then on the same Friday, you can do maybe for the next week's papers, there are 2 of them, and then we do Monday and Tuesday, different sets of people to prepare for those. And then you have like Wednesday to Friday for you to personally go through whatever you did through the 2 days. And then Friday now to like put it all together.
Okay, so that's 2 nights in a row.
Huh?
That's 2 nights in a row.
2 nights in a row, Connor.
Not 2 nights in a row. Me, I'd rather let's throttle it up Monday, Wednesday, give a break and meet on Saturday to discuss.
Kuna SPS kwa group.
I think now it's time to vote.
Okay, so what are our options?
So we have the Monday, Thursday group, on Thursday group. We also have the Moin Wednesday plus Friday quiz group.
Okay, see.
We have the Monday and Wednesday group. Yes.
Niko na suggestion, Mbona hii sikuwe the first order of business when we meet on Friday? Wacha ikuwe the first order of business when we meet on Friday because I have a feeling this is very integral to how we might need to give it some thought just to be sure. So wacha ikuwe the first order of business when we meet on Friday. But then we'll have cool heads. Everyone will be in their best position at least to discuss this matter.
Okay.
We?
Yes.
Meanwhile, tupatie all our options.
Sorry?
Meanwhile, unaweza tupatie all our options on WhatsApp, the ones we have so far, so that we know where we'll be coming from, essentially. But maybe we can make it first order of business on Friday.
Okay, but the first order of business on Friday is Nigel and
after you.
Okay then, good night, my people. See you on
Good
Friday.
night. And I have something in the group for you guys. So mnaweza angalia mwanzo. I'll talk about it on Friday.
Okay, sawa.
Kwa description ya website.
Okay, sawa. See you on Friday. All of you to click on the group description. Everything has been sent to Telegram. See you on Friday. Okay, admin kwenye WhatsApp line. You're going to be added to the WhatsApp by Joseph. Please, yes. Good night.
Fiona, nimesikia ukiongelea story ya WhatsApp. Si uniambie ni kina nani hao wajadi wa WhatsApp ni wa add cause kama iko kwa chat sitamu.
Lane.
Oh, if she has another tumwambia nitumie cause I thought I put in nilipewa.
Sasa ametoka sana nitamwambia aje shwali.
Oh, okay. I'll find it. Okay.
Okay. Just I'll also try and look for the number. But good night. Good night, Travis. Good night, Madaraka. Good night, Roba. Good night, guys. Bye.